Greetings to you. This is the second class we are having regarding the pollution monitoring and spectroscopic methods. Now, yesterday we have seen the interrelationship between the spectroscopic techniques and the pollution monitoring. We also saw a little bit about the structure of the atoms, in which we elaborated that the basic fundamental particles with are electrons, protons and neutrons, and even though there are other matters, subatomic particles which may or may not have independent existence, for the spectroscopic purposes I think the basic structure of atom as containing electrons, protons and neutrons are more than enough for our purpose. Now, today we will continue our discussion on the interaction of electromagnetic radiation with matter. The slide that has come up in front of you is it states that electromagnetic radiation is basically an energy wave travelling through the space unaccompanied by the matter, that is radiation. For example, if you wish to see light travelling, it does not have a mass. So, it is just a form of energy and that is travelling through the space unaccompanied by the matter. So, how does this energy travel through the space? Basically, almost all the electromagnetic radiation traverses either as waves or as small bundles of energy or particles, bundles of energy particles called as photons. You can consider both views. Newton had proposed that light moves as waves, and subsequently it was also proved that light also can be considered as a small bundle of particle contained called as photons. So, in classical physics, electromagnetic radiation is basically a force field in which the radiation is characterized by the frequency, velocity and intensity. For example, if we say that I have a wave, a electromagnetic wave corresponding to 490 frequency and its velocity is 3 into 10 raised to 10 centimeters and its intensity is so many lumens. So, the length is the unit for frequency and distance is the unit for velocity, distance covered by per unit time or something like that, and intensity is the amount of energy that the bundle of energy what we have been discussing. So, basically it is characterized by an electric field and a magnetic field. Electric field is denoted by E and magnetic field is denoted by H. Both any electromagnetic wave, whether it is cosmic ray or gamma rays or X-rays or ultraviolet rays or visible rays, infrared rays, microwave, any of the radiation that we consider must be accompanied by an electric field and magnetic field. Okay. These fields are in perpendicular direction to each other in general. I will show you a photograph of this field vector, and in practice both vectors are present at all orientations perpendicular to the direction of propagation. That means, if the light is travelling like this as a bundle of energy, the force field will be all around it. The light field will be passing through the center and force field will be on the left side, right side, up, above and below the field of propagation. That means, if the light is travelling, the force field also will be travelling along with that. If we consider light as a photon, on passing through the matter, the radiation may interact with the particles of the matter having electric or magnetic moment, resulting in a transfer of energy from one to the other. What do we mean? Basically, we are talking about light energy passing through. Light can pass through either in vacuum or in a air field or in air. It can also pass through solid materials like glass and other things. So, if we are talking about a light travelling in a particular medium, the medium may not contain anything, that is vacuum. The medium may contain air particles, sulfur dioxide, gas particles, gas molecules, etc., sulfur dioxide, carbon monoxide, nitrogen dioxide, ozone, and all these gases are present in our atmosphere. So, if the light is passing through an Earth's atmosphere, it has to pass through all these medium containing different gases. Now, these gas molecules are made up of atoms, which are again made up of protons, neutrons and electrons, and the gas particles, dust particles also will be there. They also will have certain amount of mass, and then electronic structure containing electron, photon, neutron, etc. And the electromagnetic radiation that passing through any of the medium will interact with these particles unless it is vacuum. So, if there is a matter present in the path of the light electromagnetic radiation, there will be transfer of energy either from the electromagnetic radiation to the particles or from the particles to the electromagnetic radiation, either way it can happen. So, that is what we have been trying to say here. So, all electromagnetic radiations are therefore characterized by wavelength denoted by lambda or frequency, that is V. The term wavelength is defined as the distance between successive maxima or minima. Now, you remember that I discussed that the light particles will be going like these waves, and the successive waves, distance between two undulations or crests or the troughs. When a wave goes like this, there will be a trough as well as a crest. So, in between the distance between the two successive maxima or minima is termed as wavelength, that is the distance. The frequency is number of cycles, how many crests appear or how many troughs appear in a per unit time, that is per second. So, the wavelengths and frequency are related by lambda is equal to velocity divided by the frequency. Here mu is the frequency and v is the velocity. So, the velocity of propagation, all electromagnetic radiations in general have the same velocity through the vacuum, that is 2.9979 into 10 raised to 10 centimeters per second. So, calculate the approximate this thing, frequency is expressed as number of cycles per second, or where it is also denoted by wave number, that is denoted by mu bar, that is written here, and the mu bar wave number is given by 1 over lambda, that is wavelength. The distribution of the spectral density intensity in a black body radiation was explained by Max Planck in 1900 by uniting the corpuscular theory, that is light made up of photons as bundle of energy particles, and wave theory is a relation between the energy of a quantum radiation to the frequency as given by this expression, that is delta E is equal to, that is energy is equal to h mu. H is Planck's constant, mu is frequency, mu is also given by velocity of light divided by the wavelength. So, this is a very famous equation, and the interaction of matter with radiation, therefore, it involves the exact quantized energy, because it is not a continuous energy as of now. Every elementary system, whether nucleus or atom or a molecule, thus has a number of quantized energy states, and absorption or emission of energy must take place only if the energy of the matter is equivalent to the distance between the energy states. Okay. So, if it is not matching, if the energy of the two states does not match with the energy of the radiation, then there is no interaction. It will just pass through the matter without showing any change either in the velocity or in the energy or something like that. But if there is a matching between the energy states as described by Planck's theory, that is, energy is quantized in discrete energy levels. So, in between there is a gap of energy, and that gap is not occupied, that space is not occupied by any particle or any transition during interaction. So, the radiation is transmitted without any change if it does not match the quantum requirement. Okay. So, the energy or frequency which the incoming photon is absorbed is given by this energy is given by Bohr equation, that is h mu is equal to h c by lambda, that also should be equal to energy of the final state minus the energy of the initial state of the substance. That means, we assume that the electrons occupy particular energy levels. One energy is EI, higher energy is EF, and the difference between the energy difference between EF and EI is given by h mu, that is h c by lambda. In the case of emission of energy, this much amount of energy is released. So, again, whether it is absorption or emission, between two states of energy levels, the energy absorbed is same as the difference between the two states, as well as if it is emitted, again the energy difference is exactly the same. That is again given by h mu h c by lambda. In this case, it is energy of the initial state minus energy of the final state. Now, when we refer to EI and EF, that is energy of the final and initial states, if it is emission, the final energy state will be at a lower energy, and if it is absorption, the final energy state would be at a higher energy level. The only difference between the two, between emission and absorption. In practice, therefore, what we say? In practice, whenever a radiation of multiple frequency, that means we are not talking of a single energy of a single wavelength. I am talking of a bundle of energy coming like this, a bundle of energy going like this, containing energies of different frequencies, different wavelengths. For example, the sunlight, what you see is a bundle of energy containing multiple frequency. Similarly, if you see only a blue light, it means it has got only single frequency. White light, in general we know from Newton's theory that it contains about 7 different colors of the light. Apart from that, there will be different energy electromagnetic radiations which are not visible to us. They may be cosmic rays, they may be gamma rays, they may be UV rays, but they are not visible. So, if I am looking at a source of energy, electromagnetic radiation coming from the sun, it will be a bundle of energy. So, this bundle of energy will have multiple frequency. If such a radiation interacts with the matter, part of it may be absorbed, part of it may be used for emission, part of it may be reflected again, part of it may be refracted, part of it may be diffracted, or part of it could be scattered away. So, there are different kinds of interaction will take place when a multiple energy radiation reacts with the matter. Therefore, we can write a very simple expression like this: total energy E refers to energy of absorption, energy of emission, and that is energy of emission, part of it is reflected, refracted, and then diffracted, scattered, and there may be so many other interactions which we may not be going into details right now. Therefore, various types of quantized energy changes occurring in each region of the spectrum and the magnitude of energy involved have been traditionally used for a variety of spectrochemical techniques. That means, what we are saying is the quantized energy levels, because they occur at particular energy difference, and the energy difference between two states are different for different kinds of molecules. Any transition that can be occurring could be the characteristic of the substance. Therefore, such transitions have been used for as a spectrochemical technique. The energy ranges, normally we always say it is gamma rays, it could be X rays, it could be UV visible, it could be infrared, it could be microwaves, radio frequency rays, etc., etc. The absorption of radiation occurring at different wavelengths and associated spectroscopic techniques, I have given them in the next table. Okay. So, you can see that I am going to the table right now. This is the table of visible range. Okay, here you can see I have put wavelength on the left side, transmitted color and complementary hue. So, this is 380 nanometers, that is less than 380 nanometers, that is considered as ultraviolet. This I am talking only about the sunlight basically. Okay, what colors we see and experience in our day to day life. For example, from 380 to 435 wavelength, if an energy of radiation contains wavelengths between 380 to 435, what you will see, it will transmit violet light, and what you will be actually seeing would be yellowish green. Okay, that means what is transmitted, remaining is absorbed. So, what it absorbs is the color what we see, that is what we write it as complementary hues. It is HUES, hues. So, from suppose it contains 435 to 480 nanometers, it will transmit all blue colors, and the remaining colors that are not transmitted are absorbed, and it will look yellowish yellow color. Similarly, if we go down the visible range, that is 480 to 490, we have greenish blue transmitted color, and it looks somewhat orangish. So, if a substance is looking orange to you, it only means that it is transmitting greenish blue color and absorbing all other colors. The combined effect of all other colors that is a substance is showing is orange. It is not the transmitted color. Similarly, if we go down 490 to 500 will look bluish green, but will transmit bluish green, but it will look dark red to you. So, and 500 to 560 range nanometer, it will transmit green and it will show you purple color, and 560 to 580 yellowish green, and it will look violet to you. You are all very familiar with all these colors, which are I am showing you as complementary hues. These are all colors of the rainbow. If you have ever seen a rainbow in your in the sky, you would see that yellowish green, yellow, orange, red, purple, violet, blue, green, etc. All these colors are visible in the rainbow. Similarly, the remaining ranges, yellow, orange, red, near infrared, etc. all these colors are visible to you. All these colors are visible to you. So, it must be noted that when I go back to this, the range is not exactly sharp. It is 380 to 435, does not mean it is exactly 435, but it could be 440, 445 like that. The range is not sharp at any wavelength, but rather they merge into one another in a diffused manner like a rainbow. And the absorption of radiation normally involves transfer of energy to the medium, and this process is a specific phenomena related to the characteristic molecular structure. For a given excitation process, a molecule absorbs a discrete quantity of an absorption line. However, since a group of molecules are existing in number of vibrational energy levels, I cannot pinpoint that the energy is only will go only through that process. Therefore, if a number of atoms are present in number of vibrational energy levels, what I normally see is a vibrational energy level is also associated with number of rotational energy level. I will show you a diagram regarding that. So, any energy level is called as electronic energy level, and then each electronic energy level is associated with number of vibrational energy levels, and then each vibrational energy levels is associated with number of rotational energy levels. So, when I am talking of electronic energy level, it means I am talking of a number of vibrational and rotational energy levels associated with each of these, and every molecule can be in any of the electronic energy level may be same, but it can be in any of the associated vibrational and rotational energy levels. Okay. So, each of these molecules will differ by a small amount of energy. So, therefore, if I draw an absorption of a substance, it will appear like a band, a big curve, Gaussian curve, instead of a sharp peak, single line peak. Okay. So, many atomic substances normally exist in gaseous state and absorb radiation only through an increase in their electronic energy. So, all these things there is no need to emphasize again that they are all quantized and appear in various subshells. So, for polyatomic molecules, that means a substance which is a single monoatomic, means the existing gas molecules existing as single molecule, or it may be a group of molecules, they are known as polyatomic molecules. So, for example, if it is hydrogen, then it is a monoatomic. If it is oxygen, it is a monoatomic substance. But if it is carbon dioxide, it contains carbon and 2 oxygen atoms. So, it is a polyatomic molecule. So, functional groups, aldehydes, ketones and several other substances occupy, they are all known as polyatomic molecules. So, polyatomic molecules, for them the electronic transitions involve not atomic orbitals, but molecular orbitals, because the orbital energy level for polyatomic molecules, they contain number of molecules associated with each other. Therefore, these atomic orbitals merge into each other to form molecular orbitals. So, for single atoms we call them atomic orbitals, and for number of molecules if they are there, the resulting energy levels are called as molecular orbitals. So, For polyatomic molecules, whenever we talk of transition from one energy state to another state, we call it as molecular orbital levels, and these are more complex than the atomic orbitals, because we know that in atomic orbitals s orbital is round shaped, p orbital is dumbbell shaped, like that we know very simple structures. But for polyatomic molecules, there will be several s orbitals may be merging with each other, several p orbitals may be merging with each other. Therefore, the structures actually, if you imagine in a 3D structure, they will be much more complex. Therefore, the total energy may be considered as a sum of the contributions from all states of energy. For each energy, electronic energy state of the molecule, there exist several possible vibrational states. This I have already told you, and for each of these in turn, they contain numerous rotational energy levels. Now, here in this figure, I have shown you number of energy levels. This is 1s, this is 2s, this is 2p, and then 3s, 3p, and then 3d, 4s, 3d, like that. There are different energy levels associated with an atom as well as a molecule. Only difference is for single atom monoatomic substances, we call them orbitals, and if there are number of atoms, we call them polyatomic orbitals. So, electronic transitions in organic molecules are characterized by the promotion of electrons from either bonding or non-bonding electrons. What are bonding electrons? Bonding electrons are the substances in which there is a chemical bond. As we see in many chemical structures, they will be associated with sigma bond, pi bond, like that. The electrons are bound in a particular energy level. Pi bonds, they are also bound in this thing, but there are a number of atoms, number of electrons where the electrons are free to move around the atom. So, we will see some of these structures after about 5-10 minutes. For the time being, what I want you to do is to remember is the bonding orbitals are designated as sigma bonds, and the non-bonding orbitals are designated as pi, pi star, etc. If an electron situated in a sigma bond, that is bound between two atoms, gets excited to higher energy level, then I have a transition from sigma to sigma star. Okay. Now, suppose there is a pi bond, just like in ethylene. So, there is one sigma bond and one pi bond in which the electrons are shared. Now, a pi bond is also bound to the atom, but in a different fashion at a slightly lower energy level. That also I can excite it to the next higher energy level, that is known as pi to pi star. The lower energy level is pi and higher energy level is pi star, designated as pi star. So, if not all the electrons are bound, there may be a chemical bonding, as you remember, ionic bond, covalent bond, coordination bond, etc. And then there could also be the electrons which are free around the nucleus. For example, they are called a lone pair of electrons. So, in the excited state, if not all the electrons occupy anti-bonding orbitals, even in anti-bonding orbitals, the molecule retains sufficient bonding character to ensure the stability of the system. Otherwise, dissociation would occur. So, whenever we talk of a substance which is having higher energy level, that means the molecule is at a higher energy state, excited, but it is not completely dissociated. Okay. So, this means that energy is excited, that means I have used part of the energy of the electromagnetic radiation to increase the energy level to higher state, but still the molecule is intact. The moment I take off my energy, that is electromagnetic radiation, it will revert to the ground state and be stable. So, the electronic transitions possible in UV and visible spectrum are basically designated as sigma to sigma star, pi to pi star and n to pi star. These are n means non-bonding electrons. The energy required for these transitions, it decreases in the same order as shown below. Now, saturated hydrocarbons, alcohols, chlorides, all these are different organic compounds that we come across in our day to day life. So, the electronic energy, excited energy levels involve large amount of energy. This you must understand. Whenever we talk of ultraviolet or visible absorption spectrometry, we are talking of electronic excited energy levels, excitation only in the electronic range, that is the range from 35.71 kilocalories in the visible range, but it can extend up to several hundred kilocalories in the far ultraviolet range. So, each electronic level associated is associated with several vibrational energy levels that I have already told you, and each vibrational energy level is associated with number of rotational energy levels. So, consequently, the absorption arising out of this transition would be most intense from 0 to 0 to 1. So, that will be most intense, and this tendency is enhanced in the liquid state, where vibrational energy levels are dampened by the electromolecular and interactions, and a broad absorption band results. So, sigma to sigma star transitions are very energetic and are found only below 200 millimeter, that is 200 nanometer, that is in the vacuum ultraviolet range. So, in general you do not see sigma to sigma star transitions in which all the valence electrons are present. So, pi to pi star transitions, you will see them in the visible range, ultraviolet range, etc. In addition, you will see non-bonding transitions, that is electrons not involved in bonding, but they also get excited to higher energy level, that is pi star. N to pi star is a very well known example. Many of these reactions are also known as the charge transfer reactions. So, such things are also visible in ultraviolet and molecular spectroscopy, which we will be dealing with in our next session. Thank you.